Alright, so first, on the calculations of Gary's experiment, potential experiment, the laser bending prediction, and the calculations for the velocity that Gary accepts as real enough to use, which is the velocity of the Earth around the sun. He and other people seem to be missing the fact that the Earth is spinning, right? So, one time a day, the Earth is shooting through space like this, and you're on this side of it. And it's shooting like this, and you're on this outside. And so the velocity is this way. Then you spin around. Another part, you're on the inside. And east is pointing the direction west used to point in space. Right? So within one day, you will get deflection from the velocity being eastward, and then 12 hours later it being westward. And during the intermediate time, it'll be coming from basically an angle in space, which is some latitude in the ecliptic, relative to the ecliptic in the solar sphere. Just the same path a star on that line would take until it's from west to east, east to west, so to speak. All right. So back to what Gary had said is and this is the proportionality of it. We were talking about you have a barrier, you have a laser. If these things are at rest, then we both would say the laser will go and hit this spot. Okay? Now, and what Gary had said, and as far as it goes, this makes sense, is but if this whole thing is moving, so this is all hooked to a spaceship, it's all inside a spaceship, right? And this spaceship is moving this way, he said, at half the speed of light, 0.5 c, right? And what's going to happen is the ship is going to go forward, half the distance that the light goes. So the light is, we're measuring from here to there, then half that distance, that's how far the ship will have gone. It'll have traveled over here. The end of the ship will now be here. Half as far as it went. And it doesn't matter how far that is. If this is a foot, then this is half a foot. If this is a mile, that's half a mile. Because it's half the speed of light. So the percentage need my little eraser. You probably can't hear this either, huh? Is it working? Probably not. How's this? So the point, to repeat the point, if the ship is going half the speed of light, then this distance here is going to be half of this distance. This is the light travels up here. It makes it that far going the speed of light, so half of that distance is how far the ship will make it going in this direction. Right? Probably be better if I had a bigger one of these. This is awkward having this here. I'm just trying it out. Okay. So for showing the object, and the thing is shot here. Let's make this a little bit longer. And half that distance is the same as how far
the x will have gone. So the x will go this same distance and be here. Okay, this is at time 1 and this is at time 2. From the point of view of the ship, therefore, goes this distance, half of that distance back here. It'll seem like it's shot in this direction. Really, Gary's model, it's going up and the ship is sliding out of the way. So from the point of view of Gary's idea of absolute space, the ship is going to move over to here. This thing's going up, and this is the spot back here that comes in time, right? This spot back here. And this is, in our model, this was 1/2 c because this is at the velocity of c. But in our case, for our experiment, we have c is about 300 million meters per second. The Earth going around the sun is 30,000 meters per second. If you see, using the 300 million number, you can run it through a calculator if you want. What you're going to find is that this 3 has 4 zeros and this 3 has 8 zeros, which is going to leave you 4 zeros if you divide the smaller number by the bigger number. So E of V over C is 1 over 10,000. So not 0.5, but 1/10,000. That means the amount of deflection that we expect is going to be the deflection of 1 in 10,000, right? So a mile is something like 5,280 feet. So 5,000 feet is a little less than a mile. A couple hundred feet less than a mile. 1/10,000th of that is easy, right? 1/5,000th would be 1 foot. 1/10,000th is going to be a half a foot. 1/2 foot of deflection in a mile. In a half mile, it'll be 1/4 of a foot. In 1/2 mile. Right? Do you see what I did there? Half a mile, half of a half. It's 1/4. In a 1/4 mile, it's going to be half again. In a 1/4 mile, it'll be 1/8 of a foot. So in a 1/4 mile, you're still above an inch. If you go 1/8 of a mile, you have a number that is 1/16 of an inch of a foot, which is a little bit less than an inch. That's with 1/8 of a mile, which is a few hundred feet, right? To divide this down. This one is 2,500 feet. No, this is 5,000. This is the 5,000. This is the 2,500, which makes this 1,250. So in 1,250, you still have about an inch of deflection. So those are the numbers that apply to the deflection in Gary's theory from the velocity of Earth. Now, his other question, where the hell, has to do with diffraction. And what the hell are you even talking about, diffraction? Diffraction isn't a thing. Look, diffraction is a phenomena that applies to waves. If you shoot something through the slits or around a corner, you'll see diffraction. That means it's a wave. If you're shooting BBs or bullets, you won't see diffraction. It means it's particulate. The weird thing, of course, about photons and electrons is that they show both behaviors. That's the thing that's hard to wrap our heads around. So here's a picture in a ripple tank of water wave diffraction. A single slit, flat waves coming up. What we mean by diffraction is the fact that it could come off at this angle here so much, right? That when it comes through here, it curves out and starts to make these circular waves. If this is really wide, it'll still cone out, but the waves might remain very flat looking in the middle. If you want to figure out what the waves will look like, you could just pretend that every point on the wave is like a droplet being dropped in, and if all of those circles were overlapping, what would it look like? And you can run the math for that. And please notice, see this relatively still part? There's this they're not even because of water is a very noisy medium, and these are effects best seen with a single wavelength like you can get with a laser, because laser is wave-like. These are blurrier because water is inherently noisy with waves. The speed of the wave changes based on the depth of the water, which means if waves overlap, then the water's deeper there, and you'll get very weird effects that add noise. So you can't just have waves in water very easily that are just one wavelength. Certainly not after a while. But even if you start off with a perfectly still tank. But notice nonetheless you have what with the screen, these are the dark bands where the wave isn't being reproduced. That's the diffraction of waves. This is what we mean by diffraction. We don't mean changing position per se, because you can also change position in waves with reflection, something particles can also do. You can which we call an elastic collision in that case. You can also change direction with scatter. You can also change the direction with refraction, where the wave is going through a different material. In water waves, that can just be water of a different depth. For sound, it's going into a different material. For light, also going into a different material affects that. So this is the answer. This is what we mean by, yes, people have diffracted water waves, and yes, you do see the effects of diffraction. And these interference effects is because even these straight waves down here are interference effects. How do you suppose you keep a wave going straight? It's because all of the waviness, which is naturally ripply, if you add it all up together, it'll stay as a line. If you take a line of drops, if I dropped a line of drops into some water, I'd expect a planar looking wave going out. Even though each drop is creating a little circle, if they're all right next to each other, then it would send everything out at the same speed, and you would see this thing that looks like a plane. But the fact that plane waves hit this barrier, bend out, and start to become curvatures, that's diffraction. You generally not see these bands because you have to be very, very careful to see them in water. It's much easier when you have a laser and you have a monochromatic wave that's an exact wavelength. But regardless of the interference caused lines here, but all waves are caused by interference. That's what propagates the waves. It's just a property of all waves that they are interfering. But besides whether or not you can see the diffraction lines, it's this curvature. That's the original diffraction, is the fact that when a wave hits an opening, it'll curve. If it hits an edge, it'll bend around a little bit. Right? Bullets don't do that. Bullets don't go here and then start bending that way that much, or at all. They could hit here and scatter and shoot off here. They could hit here and hit anything that's in the shadow here, but they're not going to come from here and then whip around that corner.